Um, Hi, my name's Ben Getchell. I'm an engineer at the Software and Application Innovation Lab here at BU. We do a lot of collaborative work with the MOC and Red Hat. And I'm going to talk today about Conclave Cloud Dataverse, which is a system we've been implementing on the MOC over the past year. So we'll start off with some motivating examples. Hospitals may want to join their records on emergency room visits to see, as a whole, larger trends on trauma room visits within the Boston area. Or they may want to pool their data across one another to, get more accurate statistics on rare diseases that they each hold individually. So historically, this kind of work hasn't been possible due to patient confidentiality laws like HIPAA and legitimate privacy concerns. And so this issue isn't specific to medical data. Often, the more value that can be gained from piecing data together, the more cautious that contributors become about participating in a computation over it. So this is due to the financial and legal and personal harm that can be done in the event of a data breach. So there's this myth across data science that we need to choose between the real social and scientific good that can be gained from sharing data and the privacy and confidentiality of personal data that we care about. But this myth doesn't actually need to be a reality in a lot of cases, at least. Secure multi-party computation is a cryptographic technique that's been an active area of research since the late 70s. It allows data to be shared and computed over between parties without ever being revealed to anybody else in the computation, so only the result is delivered. Using MPC, then, we can completely rethink how we go about doing data analysis in general. Rather than basing the kinds of questions that we want to ask around, what kind of data is possible to acquire in the first place, we can flip that whole workflow around. We're able to instead figure out, what kind of questions we would want to ask if we had access to any data whatsoever, and then figure out how to adequately protect that data in order to respect whatever kind of privacy concerns exist for the input parties. So going back to the C2D framework. We want to bring this kind of privacy-preserving scientific data analysis to the open cloud, or to the MOC. So Dataverse, which you've heard about a few times today, is one of the largest public repositories for social science data in the world. So it's already been integrated into the MOC by separate researchers, and it fits very nicely within the C2D framework. It allows fine-grained and extensible access control policies on uploaded data, and it allows us to compute analytics directly in the cloud, so the data never needs to be exposed beyond the protected enclaves where it lives. So Conclave is a tool for doing MPC that other researchers and myself have built over the past 2 or 3 years, and it functions as our backend for MPC computations within C2D. So in practice, MPC has encountered several barriers to more widespread adoption. It's difficult to implement, and it requires a lot of specific cryptographic training in order to be done correctly. Further, most tools for doing MPC, you can only do so through the use of domain-specific languages, so it makes it kind of impractical for an everyday data scientist to use. MPC also tends to be heavily latency-bound, since it requires an enormous amount of messages to be sent between parties throughout the computation. And it typically scales really poorly to realistically sized data. Typically doesn't scale beyond maybe 10 gigabytes or something like that. So many real-world workflows, though, don't actually need to be computed entirely under MPC to respect the privacy concerns or the privacy guarantees that you would expect from multi-party computation. So with this in mind, Conclave uses static analysis to decompose and reorganize workflows such that as little MPC is done as needed, so there's a lot of local work done, and then it'll submit that local work to an MPC job between the parties, and then maybe do some more local work afterwards. Our implementation of Conclave connects to existing backend data stacks like Spark and Hadoop, and the code's publicly available on GitHub there. So we've already built a prototype implementation of C2D on the MOC that works within a single OpenShift project. C2D runs on containers, so each container stores data associated with a single data owner, and the containers never share data in any form that can be reconstructed between one another. So all the messages that they're sending to one another regarding the data can't be reconstructed to the original data at all. and the containers themselves and the volume storage is deleted after the computation terminates. So this ensures that the data can't be retrieved later on afterwards. So this is a high-level picture of how C2D works. A user submits a workflow along with endpoints for the data. We're currently using Swift, but we're implementing Dataverse. I'll talk about it later. So they submit that via our web portal, a workflow and endpoints for the different data sets that they would like to compute over. The web portal ingests this information and spawns a unique pod for each input data set within that OpenShift project. So each pod running a containerized version of Conclave downloads its input data from Swift to an empty dir located on the pod. We chose empty dirs because it's ephemeral storage, so it gets deleted when the container gets deleted and doesn't stick around, so nobody can pick it up later. Conclave will then generate the necessary code, both for the local and the MPC backends, dispatch it accordingly, and write the output data back to Swift, where it can be retrieved by the user. So it's important to note that while the pods communicate with one another both for workflow orchestration and for MPC, no data from any pod is sent that can be reconstructed by the pod that receives it. So we anticipate that researchers would not want to expose their data to C2D if they can't restrict the kinds of analyses that are going to be performed over it. So selecting out if you just selected out a single row in a data set, even if you did that entirely under MPC, that would just leak the row. So I mentioned earlier that Dataverse's access control policies are easily extensible, and that's exactly what we needed in order to provide this kind of functionality. So we haven't implemented this yet, but it's ongoing work. Researchers will be able to indicate, for each column in the data set, which kinds of analyses or which kinds of output that they're going to permit from the data stored in that column. So in order to do this, we need to first integrate Dataverse within C2D, which is also ongoing. And then finally, we intend to support computations across OpenShift deployments. This way, each pod involved in a computation, instead of all running within one OpenShift project where it could just be viewed when the data gets decrypted on that pod, the pod will be in an OpenShift deployment that the data owner trusts. So this way, even during the computation, when the data sits unencrypted on the pod, it still can't be viewed by anybody. So to sum up, MPC has the potential to alter the way we think about data science and data analysis in general. With MPC, we wouldn't need to choose between data sharing and privacy concerns, and this can be leveraged to gain unique insights that would be otherwise impossible. In C2D, we believe it'll bring this kind of functionality to the MPC because by bringing MPC to the cloud where the data already lives and abstracting the cryptographic details away from the user, we can make MPC accessible for a lot more people. And that's it. That's good. Sweet.